name is Chen Bing. I come from Vietnam. Vietnam Academy of Science and Technology. So first of all, I would like to thank the organizer for inviting me to participate in this APEC Forum. So this is my first time to attend such kind of forum. So actually, I don't know how to present my talk because quantum in Vietnam is in initial state and you don't have much material to present. So my talk will be very short. So first I would like to make some overview about the organization structure in Vietnam. So in Vietnam, you have the Vietnam government, and below this you have the different ministry. For example, Ministry of Science and Technology and Ministry of Education. In Vietnam, we have also two academies. One is Vietnam Academy of Science and Technology, and the second one is the Vietnam Academy of Social Science and Humanity. So related to quantum, you have the Ministry of Science and Technology and Ministry of Education in Vietnam Academy of Science and Technology. So the Ministry of Science and Technology is to perform the state management on all science and technology in Vietnam. This ministry also oversees the so-called VTIS, is Vietnam Korean Institute of Science and Technology. So this is a collaboration between Vietnam and Korea for science and technology. So this institute is somehow the copy the system of the KRISS, Korean Institute of Science and Technology. But this institute, so far I know, they don't have much to do with the quantum science and technology in Vietnam. And second, the Minister of Science and Technology also have the National Foundation for Science and Technology Development. So this foundation is called support all research and project in Vietnam. The Minister of Education performs the state management on university. So the two biggest university in Vietnam is the National University. One is in Hanoi and one is Ho Chi Minh City. This is the name of Saigon in former time. So my working place is Vietnam Academy of Science and Technology. So this academy belongs directly to Vietnam government. And within the Vietnam Academy of Science and Technology, we have over 30 institutes and centers. But the two major institutions have to do with the quantum. It's the Institute of Physics, where I am working here, and the Institute of Material Science. Besides the institutes, these two institutions, you have also University of Science and Technology. So this university is some collaboration university between Vietnam and France. So sometimes you call this the France-Vietnam University. So they are more or less the same. Centrally in Vietnam, the quantum is somehow it's in initial stage. So you only recently you have some few months ago in June 2025. Government have issued a list of strategic technology. So this list includes the quantum technology. So far you have only few months, and you don't have the progress yet. So to respond to the government program, the Vietnam National University at Hanoi and Institute of Physics started some project to do for quantum technology. So in the May 2025, Vietnam National University founded the Institute of Quantum Technology. So this is the first institute for quantum technology in Vietnam so far. So these institutes, they want to study quantum computing, quantum information, and quantum sensing. This institute have founded only a few months ago, and you don't have the results. But they have the plan in 2030. They will try to build the 5-qubit chip made in Vietnam. So far, I guess that they will use the superconducting material to build this chip. Our Institute of Physics have also some project to do on quantum science. So, but next year you will start some project on photonic experiment. They try to make some single photon transmission, but this test you still don't have the result yet. But next year maybe you have something to show. But as an Institute of Physics, you have to do a lot on theory because Vietnam is a poor country, and then you don't have so much money to do all experiment. In theory, you do the quantum simulation, quantum material, and quantum information as our institute. Our Institute of Physics is a physics department of Vietnam National University. Have tried to build a bachelor program on quantum and science technology, but this program is still considered by Minister of Education, and you hope that in the next year you can make some admission in the fall semester. So far, because the quantum in Vietnam is the initial state, and you feel you are lagging behind other countries in research personnel, in research equipment, and in training programs. But for research personnel, now you are trying to send students for abroad study and to attract the foreigner to come to Vietnam to do some research. For research equipment, our government has tried to increase the N1 budget from 2% to 3% of the government budget, but this is still very small number, I think, because it is 3%, not 3% of GDP, but 3% of the government budget, so it's a very small number. And now we have the different training program, but it's only in initial stage. So this is the internal resource. You try to solve the quantum problem in Vietnam. But for international network, you try to propose something like international network for quantum science technology. This is similar to our how to say this one. This is called ICTP, Asian Network for Estimator and Complex System. So you want to do something like this network. So ICTP is the International Center for Theoretical Physics. So this network you start in 2017 and 2020. But due to the COVID time, then you have the sampling time because this, and now you start the new the second stage of the Asian network. So in Singapore, the participant country is Korea, Vietnam, Thailand, Philippines, Indonesia, and Cambodia. So is it more or less like the ASEAN country? So the sponsor of the network is the ICTP, International Center for Theoretical Physics is located in Trieste, Italy, and APCTP, Asia Pacific Center for Theoretical Physics, and so IBS, BCS in Korea. This is IBS is mean the Institute for Basic Science, and BCS is Physics Complex System in Asia. So the aim of this network is to foster the growth of advanced study in quantum science in developing countries, and mostly in the ASEAN country. Why you choose the ASEAN country? Because ASEAN country is very close to each other, and it's a very compact region. And the one advantage of this, the people in the ASEAN country can move freely without a visa. So you can go from one country to another without any problem. And so the cost in this ASEAN country is cheap. So with the low budget, you you get support and maximally participant in this network. And in this network, you organize each school in workshop in the number of countries. So, for example, in 1917, the workshop in school organized in our Institute of Physics in Vietnam, and the next one in Thailand, and the next one in Philippines, and then later to Vietnam. And this next month, the workshop in school will be organized in Philippines, and the next year, the workshop in school will be held in Indonesia. So maybe I can show you some picture of this school and workshop in our network. So the first one is in Vietnam, and then in Thailand, and then Philippines, and then in Vietnam, and then in Thailand and Philippines, and next in Indonesia. Cambodia is somehow small country, and all countries they have only 11 people for people physics, so they cannot organize the workshop in school. So ASEAN country somehow is very poor development, and you need this. So this is our center. So I am director of this center for theoretical physics as an Institute of Physics. So you do one theory, so you don't have the money to do experiment. So in this center you have the condensed matter, and then you have high energy physics. So in condensed matter you can do quantum simulation, quantum material information, and this is in what our institute. So you have time, so you are welcome to visit our institute. So maybe this is my first time to attend this forum, and I don't know how to present this is about my research. This is similar to Professor Zoller talk this morning. So you to do some quantum simulation by optical lattice, but we do only on theory, not experiment. So you can make something like simulation of quantum system by neutron atom in optical lattice. So maybe because we have a very short time, and then I will skip this. This is my talk. So basically, you try to simulate some quantum state that's in the correlated system, and there is some very strong entanglement with an electron in the system. So maybe this is somehow my research result in my group. So maybe I will skip because I think there is audience in different field, and my research is very narrow subject. So it is okay. So maybe I will stop my talk and thank you.
We'll be taking comments or questions. So what do you think Korea could be a good way for Korea to help, like train your...
Yes, I think Korea is a very good factor that can help the ASEAN country in developing quantum science, like our network in condensed matter physics. The Korean ABS Institute of Physics Science have allows, for example, for school in workshop, the specialists from Korea come to ASEAN country and teach us some lecture and exchange some research. I think the Korean is very important.
So, yes.
Yeah, I'm just curious if you can comment on any research efforts in cybersecurity, like post-quantum cryptography development.
Sorry, I did not get your question.
Oh, I'm curious about efforts in cybersecurity, like post-quantum cryptography.
Quantum computing.
Cybersecurity?
Security.
Yes.
Certainly, there is also some research of the military institutes. They interest in quantum security, but this project is somehow not open, and I don't know much, and I cannot tell you about it.
Okay.
That kind of project.
Okay, so in view of the constrained schedule, let's end the speaker on
Thank you for the opportunity to be here at the APEC Forum. My name is Dr. César CASTROMONTE. I'm a physicist from the National University of Engineering in Lima, Peru. And today I want to share Peru's perspective of quantum computing. I feel that for a country it's not just a scientific curiosity, but a strategic imperative for our future. So I will outline very quickly our opportunities, our challenges, and the roadmap that we want to take as a country to ensure we are not left behind in the next technological revolution. So I'm going to skip a few slides, and let's go here. Yeah. So to understand our approach, one must understand the country, Peru. So we are a country of immense diversity in our geography, from the coast to the highlands to the Amazon, in our economy sector, right? This diversity is our strength, but it also presents a lot of challenges. Our strategy must be tailored, focusing on applications that address our specific needs and leverage our unique biodiversity and resources, right? So, quantum opportunities. Yeah, sense. So we want to focus on a strategic sector where quantum computing can have an immediate impact, right? So in mining, for instance, a sector which is a pillar of our economy, quantum algorithms can optimize exploration and logistics for minerals like copper or lithium. In agriculture, quantum simulation can accelerate the development of climate-resistant variants of native crops like potato, corn, quinoa, and cacao. By the way, you can see a lot of potatoes there. We got like a lot of different variety of potatoes. Well, in health, it can help us to model molecules to improve our medical studies. With this, we can combat local diseases such as dengue or tuberculosis, which is still a real problem in some part of the country. Right? So, and crucially, in education, we are investing to become a regional talent hub with universities like you and I, the National University of Engineering, and some other universities, leading specialized programs using accessible cloud platforms to train the next generation. So, this effort also extends to our private sector. So we see opportunities for startups in quantum software, cybersecurity, and tech consulting. For instance, a Peruvian company could develop logistic optimization tools for the port of Callao or for the recently open port of Chancay, the biggest commercial port in South America. On the other hand, we're actively seeking for global partnership with tech leaders like Google and IBM, for example, to attract investment and enable technology transfer. Another key priority is the early adoption of post-quantum cryptography to secure our banking, government, and telecommunication sectors, turning a future threat into a present-day advantage. So, but as we recognize the opportunities, we're also quite aware of the significant challenges that we got in front. So far, we lack the infrastructure and massive investment needed to build quantum computers. As I say, building or maintaining quantum computers requires advanced laboratories, cryogenic systems, and substantial investment that at this point or currently Peru is not able to do. So, most critically, we face a talent gap in hard science and emergency technologies. So without urgent investment in STEM education, we risk falling behind our regional neighbors and suffering a continued brain drain. Furthermore, quantum computing may widen the gap between developed and developing nations without a strategic intervention. So this is what we want to do now. We got this plan so far. This is what we got. So we have basically got 5 points as a strategy. The first one is the development of human capital. So our priority is to
build human capital. So Peru needs a new generation of scientists and engineers ready to lead in quantum computing, AI, and cybersecurity. We will launch university and technical programs to create scholarships and establish alliances with platforms like IBM Quantum, Google, and Microsoft. Exchange programs with leading research centers will give Peruvian students access to the best international training. This is how we will lay the foundation for our own quantum-ready workforce. The next strategy is fostering research and innovation. So our second strategy focuses on research and innovation, as I said. We will found new research centers at the most technological universities in the country, UNI, PUC, and UTEC, to connect quantum technologies with AI application in mining, agriculture, and health. Collaboration between universities, industry, and government will be essential. To sustain innovation, we'll establish a national fund supported by both public and private sectors. This will help Peru move from technology consumer to technology creator. The third strategy aims at applying quantum technologies to real national challenges. Pilot projects will target mining optimization, genomic research in agriculture, molecular modeling in health, and cybersecurity for the public sector. We will promote post-quantum cryptography to protect sensitive data in banking and telecommunications, and will help small businesses adopt advanced technology through target incentives. In short, we want innovation to reach every productive sector of Peru. The fourth strategy focuses on building infrastructure. We will establish quantum laboratories in Lima, Arequipa, Trujillo, and Cusco, the main cities in the country, all connected through cloud-based simulators. Expanding 5G connectivity will support AI and cloud computing applications nationwide. We also plan to acquire academic and industrial access to platforms like IBM Quantum or AWS Bracket. This network will ensure that Peruvian researchers and students can experiment, test, and innovate on global level. And finally, the final strategy focuses on policy and collaboration. We will create a National Advanced Technologies Agency under CONCITEC. This is our funding, science and technology funding agency, to coordinate this long-term plan. Fiscal incentive will encourage private investment in R&D and technology adoption. And through agreement with NIST, the Perimetry Institute, and the European Union, we will secure training technology transfer and international partnerships. This will allow Peru to grow within the global quantum ecosystem. So what is going on at my university so far? So we are not waiting. At the National University of Engineering, we are actively building local research capacity. We are working on practical innovative projects such as developing quantum sensors using nitrogen vacancy centers in diamond to measure magnetic field with high precision. We're also designing a low-cost spectrometer for nuclear magnetic resonance. This frugal innovation is crucial. It allows us to develop core expertise and create solutions tailored to our context, even with limited resources. And also, we are leading, taking our students, getting familiar with all this new technology. So, conclusion. In conclusion, Peru National Strategy for Advanced Technologies represents a comprehensive roadmap to enter the quantum era by developing talent, supporting research, promoting adoption, investing in infrastructure, and building strong policies. We aim to position Peru as a regional hub for advanced innovation. The challenges are real, from infrastructure to specialized training, but so are the opportunities. If we act strategically and collaboratively, quantum technologies will become a driver of sustainable growth, digital sovereignty, and social progress. So this vision aligns perfectly with APEC's goal, right? To build a future where science, innovation, and cooperation benefit all economies. Thank you.
Questions? Professor,
Sure.
for your talk, and I see a lot of your emphasis on optimization. Right? So, have you thought about using this so-called digital annealers to do the optimization? So basically, use classical computer just to do the optimization.
I know. Yeah, as I say, we are just exploring the different possibilities, and quantum technology is probably the next, as I say, the next revolution, technological revolution. So we need to explore it. We're using technology so far because, as I said, mining is probably the basis of our current economy. But anyway, we need to explore all the possibilities. Quantum computing for optimization and logistics is one thing that we want to do.
Okay, so yeah, in view of the time, because we're really
Thank you.
let's move on to the next speaker. So, yeah, our next speaker is Dr. Haza Nuzly. He's from Malaysia. University of Malaysia.
Hi, good afternoon everyone. So first of all, thank you organizer for inviting me and also having me here. So today I'm going to share a topic of the role of my university, UKM, in Malaysia quantum computing talent development. So a bit about myself. So my name is Haza Nuzly Bin Abdull. So I'm an associate professor from my faculty of quantum computing, and currently I'm leading a project called quantum computing for future-ready financial structure processing automation. So my detail can be seen here. So you can get my detail from LinkedIn and also my university scholars. So this is our building, faculty buildings. We have two buildings, one for academic, one for research. This is just an extract on my presentation. I'm going to talk more about my university in quantum computing talent development through some collaborations and also some teaching and research. But my slide I have to a bit so that it goes more on the Malaysia spectrum of quantum talent development. So the content of my presentation today is we're going to talk about quantum technology in Malaysia, and then we're going to see the talent development from some government agencies and also from University of Malaysia. So let's start a bit on quantum technology in Malaysia. So Malaysia, we started quantum technology research R&D, research and development, starting from 2010. And based on this EU report, impact of quantum technology on EU future policies 2018, this stated that Malaysia is among main players in quantum technology based on the patent application that we found in EU report. So we are number 6 in 2016, and also we have quantum command center and control center that operated for 3 years, 2011 and up to 2014. This is based on Kuala Lumpur, our capital city. And then at the moment we have so many policies, government policies that related to quantum technology, starting from our cybersecurity policies up to the latest one, which is the National Science Technology Innovation Policies up to 2030. Malaysia, we face quite a number of challenges in order to go beyond these quantum technologies, especially on these 6 areas: the awareness and adoption, R&D investment, global competition, collaboration and ecosystem, talent expertise and regulation, ethical frameworks. But today, I'm going to talk more on the talent and expertise problems. So this is the topic I'm going to cover today. So we have a few strategies in Malaysia in order to tackle all of that challenges. And for today, I'm only going to focus on the building of quantum ready talent ecosystem. So we're going to have this pipeline in order to come up with this quantum talent, because there's many presenters that presented this morning talking about how important is quantum talent. So let's go to the second part of this presentation, where what our government agencies are doing in order to build this quantum talent. So first, we have our ministry, called Ministry of Science, Technology and Innovation mostly. This is our main reference for all and main ministry for all this quantum technology and research and development. So they are the one who are going to formulate the policies, coordinating all this R&D, and then doing all the collaboration between industry, government, and also industry. We have one body or center under that ministry called Malaysia Institute of Microelectronic System, or MIMOS. This is our Malaysia National Applied R&D Center. That is the building located in Kuala Lumpur as well. This MIMOS we have launched this year in February, in collaboration with one of these Korean industry as well, STT. MIMOS Quantum Intelligence Center. So this is the framework of that center. So we're going to have sort of a regulatory framework establishment, and then the talent development that we're going to cover today, some infrastructure development, global awareness on this quantum funding, because this center is going to provide quite a number of fundings, and also R&D collaboration. So in terms of talent development, we have a three-phase roadmap in order to come up with all this talent development, starting from this year up to 2025, which is a 10 years framework. So the first phase is starting from this year, 2025, up to 2027, where this year is these 3 years are all about establish awareness, do some basic training, and then academic groundwork to develop some quantum syllabus for schools, our schools, and also some universities modules. And also we're going to launch a Quantum Information Intelligence Center Academy in order to establish some 500, to come up with 500 engineers by end of 2027. And then we plan to have to run first national hackathon in quantum. So this is our first 3 years of this roadmap, and then we're going to go for the second phase starting from 2028 up to 2031, where this one we want to develop after we have all this basic skill. So we're going to develop this skill workforce, and then we're going to have this innovation infrastructure on this quantum. And we plan for a few universities to come up with this Bachelor of Quantum Technology and Master in Quantum Intelligence programs. And then we're going to have all these research accelerator, and then we're going to fund for more scholarship in order to develop the talent. And then for the last part for this framework is phase 3, which is a maturity phase, we call it. So 2032 up to 2035. This one, we hope that at that time, this time we have achieved some talent independence. It means that we have our local talent in quantum technology. And then we can integrate starting from the lower academic level in Malaysia, starting from our kindergarten up to the university level, to explain about this quantum. Because in Malaysia, the science class is starting from a very early stage. Even though it's very simple, science class like about agriculture, something like that, science, life sciences, and so on. But it started from an early stage. So we hope that we can apply that type of concept also for quantum to the range of all our students. So, and then we hope that we are going to be part of this Asian Quantum Education Hub. Okay, in terms of the education, so we have two parts, which is the education program and reskilling and innovation. So for education, we start from the school. So we are going currently now developing some modules on for school on quantum logic, on the light and energy entanglement, serial games, simple cryptography labs, and so on. And then we let our school students to learn all about this KISS a bit, and then VOCA and so on, so that they have some awareness on the quantum. And then for the university level, so we go for these classes, some classes we have the core on quantum programming, and then we have AI quantum algorithms, certain classes. and then on the security part of quantum and sensing. So, and we also hope, because this is the planning, some will be applied, that we can have some certified quantum engineers. For rescaling means that the one who don't have the background of quantum but want to learn the quantum, so we have certain type of rescaling program, which is the rescaling program for 6 months by HRD. Is our is one of the agencies to retrain our citizens, mostly on for those who got retrenched to get some new skills. Okay, and many more, many type of group as well. So HRD Corps and then by Coursera and EMOS as well. So we're going to have more talents on this area and machine learning and also quantum-based, quantum enhanced AI projects. Alright, and then we have the hackathon and also the scholarship as well for this rescaling and innovation. So in Malaysia, we have one academy called Academy Science Malaysia. We have that Academy Science Malaysia. They have a special interest group, SIG, called SIG on quantum technology. I have a picture myself and my colleagues, and also the head of quantum technology for the SIG. He's the one who started the quantum lab in Malaysia, basically. So it's the Dato' Muhammad Izzah. So the project that I showed before is under his supervision at the time. Okay, so he's currently now as a SIG on quantum technology. So they are the one who developed these papers for Malaysian quantum technologies. We have a quantum machine as well at the back. Okay, and then we have an initiative by all the universities in Malaysia. So we call it IKEY. So this universities collaboration. We help the government. We invited and helped the government to come up with this policy. So I also involved with this event. So this is an ecosystem. We cover some part of quantum technology. This is my university. So starting from 1904, now 1924, it's part of whole universities. So we have 2 campuses, one in Johor, one in Kuala Lumpur. In the video of Kuala Lumpur, you can see the Kuala Lumpur city at the back. Okay, and this is just some information about our universities, and then we have the Faculty of AI and Faculty of Computing and Faculty of Science that are related to quantum research. So we have a few research in our universities. So currently I'm leading the project that I showed just now. This is the internal project within the faculties and also our industry collaborator, which is the main bank, the biggest bank in Malaysia. So to solve some problem in the banking industry. And then we also have another team, led by the Yam, and also collaboration with the NTU and the NUS to come up with this quantum processor and control systems. So, and for the research in UTM, we follow the guideline from the phase that I mentioned just now, phase 1, 2, and 3. Currently, we are in phase 1, so the initial phase. So, the university currently provide quite a big funding on the quantum project, and then develop some special interest group, quantum computing in our university, that all any faculty member can join that group. And also, we are currently producing some postgraduate students on quantum computing research, starting from the masters and then after that PhD. So this is all the research from other universities in Malaysia as well. So we have many other universities that do this quantum research. They have some specialty on this quantum research, which is I have no time to explain because due to time constraints. So it means that we have other universities as well doing all this quantum research. For teaching and learning, the quantum class been according to this phase 1. So we have to give some exposure on our students. So we have embedded some quantum computing topic in undergraduate class, postgraduate class, and then we have the project for students also that doing this quantum related project. And so we have the awareness on some talk forum and hackathon. So the phase 2, we plan in our university to have this quantum computing center, and then we have a specific undergraduate postgraduate quantum program, and then for research funding, and also we plan to have this UTM spin-off company. Our university have many spin-off company that try to commercialize our product. So we hope that we can have a company that commercialize quantum computing product as well. So by then I conclude my presentation, and thank you.
Very short comment or question. If not, let's move on to the next speaker. So, the next speaker is Frédérique from Australia. She's from New Zealand. Global Center for Photonics and Quantum Technologies.
Good afternoon. I'm Frédérique from New Zealand. Kia ora tātou no pariha aho I tupu ake o I Brussels ki oto o ki ko o te awa ki tamaki mako aho e noho ana ko Frédérique tuku inua te la koto katoa. This is the way that we usually start and introduce ourselves in New Zealand. The language is Aotearoa Maori, so that's the language of the indigenous people of New Zealand. And so it's important to share a little bit of our culture. What it says is where I'm from. I'm from Belgium. I have a river. It's called the Hoeft. And normally, when you do your PPI, your introduction, you also mention your mountain. If you have been in Belgium, you know it's flat, so I don't have a mountain, so that's why. So, and I don't live in New Zealand. I've been here. I've been there 23 years. And I know the Global Center for Photonics and Quantum Technology, and I will talk a little bit about the center and what we have done to develop quantum research in New Zealand. So basically, the Global Center for Photonics and Quantum Technology is what we call a center of research excellence. Those of you who are from Australia, you know that system very well. You have the Center of Excellence. So it's a consortium of researchers from all around New Zealand that are focusing on photonics and quantum technology. So we bring together 6 universities as well as the Measurement Standard Laboratory, and we also partner with 2 museums for outreach. So it's financed by the Tertiary Education Commission, so a strong focus is on education, especially of our PhD students. So it's really, one of our goals is really to upskill our PhD students. We have about 60 investigators across the country, 40 research fellows, and more than 100 students. And so our mission is really to advance globally distinctive research in photonics and quantum technology for the benefit of New Zealand. And when we say distinctive, is because one of our focus is to make sure that indigenous science is part of our research program as well. So, as a small country, I'm sharing a little bit the work that we are doing to kind of get photonics and quantum technology out there, and especially to talk to our government, because I'm very jealous we don't have yet a strategy for quantum research in New Zealand. So I have a lot of work, so thank you for sharing all your strategies, because we have a bit of work. So I think for us, especially because our center is about photonics and quantum technology, I always remind people, and I stole that slide from Cathy Foley, who is the previous science advisor in Australia, is that it's really at the intersection of quantum, photonics, and supercomputer that a lot of the innovation happen today, right? And it's always good to remind people that photonics is really the electronics of the 21st century. We have a lot of integration going on now. So everything that was a benchtop 20 years ago is actually now a microchip. And it's also really important to always explain people what we mean by quantum technology, right? Because we always argue, is there a quantum or photonics technology? And I think what people hear, or what we want to say when we talk about quantum technology nowadays is really when we start to use those weird behavior, as we can call them, and it's really important to explain the difference, how we can unlock those new properties and have better measurements measurements, more accurate sensing, and so on, and solve better problems with those quantum computers. So back to New Zealand, we are a small country, but we managed to collaborate quite extensively around the world. So we do have exchange with Horizon Europe, NASA, NIST in the United States, CNRS. You can hear that some of us speak French in New Zealand, so that's why we collaborate with the CNRS, but also DLR in Germany. And New Zealand, being a small country, it's relatively easy to build an ecosystem, and it's relatively easy to talk to industry. So we have strong collaboration with industry as well. Fonterra is the milk producer of New Zealand. It's probably #1 in terms of industry in New Zealand. We work with the healthcare in New Zealand, Te Whatuora, Aerospace. So New Zealand has recently developed a very strong aerospace ecosystem. And then we also have spin-out like Southern Photonics that works intensively with the US as well. We recently have had a good history of having spin-outs. They're mainly in the photonic space, and I will mention them again later. So we have Proventis, which is about prostate cancer detection, Luminoma, which is about skin cancer detection, and Gender, which is about sperm sorting for the dairy. We are a farming country, so a lot of the applications for us are often related to farming or agriculture. Right? Everybody loves the land in New Zealand, the land from New Zealand. And New Zealand is actually, because it's small and it's well connected, it's actually a really good country for a startup to start, because it's well connected, and so people find it a little bit easier. And so what we are working on in the Global Center for Photonics and Quantum Technology is really to create that pipeline. We really want to be a deep tech center, and we want to be rooted in fundamental science, and really explain how long it takes for those ideas to come to fruition and spin out. And so it's really important to keep that message that yes, we have a lot of spin out in quantum technology now, but that's because people have invested a long time ago in fundamental science. And that's when it's important to remind ourselves that in New Zealand we have a strong history of excellence in photonics and quantum technology. We are called the Global Center because Jack Dutch in the 80s, I think, and Dan Walls in the 80s as well, were world leader in quantum mechanics and quantum optics. And so that's really why in New Zealand we have that strength now. That's one of the reasons I moved to New Zealand. And so our strengths now, like most people in quantum technology, are around communication, computing, and sensing. Because we are a smaller country, we're not building quantum computer, we are building parts of a quantum computer, or we are a very niche country. That's really the way we excel. It's by having niche applications. So what we are excellent for is quantum memories for secure communication and sensing and distributed quantum network. We also do classical memories for quantum computer. We have a strong research program in KRISS optical communication. Some of it is in collaboration with DLR in Germany and with Australia as well. In computing, we do a lot of transduction, so that's one of our strengths, is converting microwaves photon into the optical domain. And we also work on an IC machine, which is a way to build a computer for the poor in some ways. In sensing, we focusing on sensing, especially in agriculture, for agriculture and health. But also New Zealand, you might have heard that we have a lot of volcanoes, a lot of earthquake, and therefore a lot of tsunami risk. And so a lot of the sensing we do is for geophysics. But also for extreme environments, so we have sensing for space, so for like power generation in space, for example. But also sensing, for example, to help understand the measurements that are done on Mars, right? So you get the signal from Mars, but because the environment is quite different, you need to have to simulate that environment in your lab so you can understand what's going on when you get the data from Mars. So this is photonics and quantum technology in New Zealand. Recently, the government gave us an additional 12 million, and then just recently 1.5 million for what they call a catalyst fund. So the catalyst fund in New Zealand is a fund dedicated to international collaboration, and we have 6 target countries: the US, the UK, Germany, Singapore, and Japan. So any one of you in the room who are part of those countries, talk to us. And so we just announced the main trench project for the next 3 years. We have 7 projects, but just 3 of them is, like, one of them is what I mentioned before, seismic detection so it's basically using optical cable that are in the sea to detect tsunami. And so we have the transduction project, but also a supercomputing approach as well. And so what we always remind people is that photonics and quantum technology actually underpin a lot of the technology. I was like, wow. So yeah, photonics and quantum technology is really a good way to enable the economy in a country. And we steal another thing from Australia. So they stole the pavlova, they will understand the joke. So we invited Katie Foley to help us do the quantum meets. So the quantum meets is something that Katie Foley did a couple of years ago in Australia. It's really get people, especially from industry, in a room, tell them about quantum technology and look at how quantum technology can help businesses and get some idea. But it's also a very good way to educate people about photonics and quantum technology, or just quantum technology. Because often when you talk to people in the public, they don't really know what you mean with quantum technology. It was a huge success. We had 120 attendees, and now we're getting more and more questions, and we can see that there will be more and more projects coming out of those initiatives. So, for example, we talk about diagnostic for non-communicable disease, sensing of infrastructure, monitoring of food product quality, because New Zealand is a very big food producer, explaining them exactly what we mean by quantum computing, what kind of problem you can solve with quantum computing, on-farm sensing. So that was really good to bring awareness to the industry ecosystem about what we can do and the fact that we can solve some of the issues with quantum technology. So just a few more words about some of the strengths we have. We have a very strong core of people doing laser source and microcavities, photonics and in the photonics and quantum realm, and we have a lot of international collaboration on that. And that's where we do, for example, quantum information, random number generator, and working on photonics integration. We also have a lot of sensing and imaging for healthcare and agriculture, and that's where we also looking at ways we can 2.0 a lot of the technology we are using at the moment. What we have, we really have a deep tech pipeline coming up. So the Domo Center was only funded in 2015, and that's a message that I try to give very strongly to our government, and I think it's really important for us to keep that message, is that it takes a bit of time when you start by funding fundamental research, building that capability in a country, when you start to get decent rates of spin-out. And so we are there with the photonic spin-out from the Domo Center, and now we hope that in the next few years we can already identify some of the quantum spin-out. And I think it's really important, I know it's really important to keep that message that deep tech doesn't give you money overnight. And Quantum Australia has done a report on quantum technology, the quantum industry, with an association with the optics, the Australia-New Zealand Optical Society. We've done a report on photonics and quantum technology. And I think it's really important to show that when you get that pipeline right between fundamental to spin out, you can really sustain a big part of the economy of your country. And as I said before, we are a small country, but we are a beautiful country and really keen to collaborate with more people. Talk to us. We have a lot of opportunity. There is a call open at the moment for Korea on quantum communication. So that's only for with Korean collaborators, but we have other opportunities coming up all the time. And we're always happy to see you. We have a symposium every year, and this year, NSCOP is in New Zealand in December. So if you want to be invited to our symposium, reach me.
Short question or comment? So do you consider Australia a foreign country? Or
I think sometimes it's useful for us to be the third island, especially if we can share more facilities or collaborate with Australia. But we are Kiwi. We are different. Ask them.
so our next presenter is Mr. Rattakorn at this session. He's from Thailand.
안녕하세요. Thank you, GPS, for this opportunity for me to give a talk in this event. In this talk, I will talk about the quantum metrology project at NIMT and also some story of Thailand quantum technology program. Emerging of quantum technology actually put a lot of challenges to Thailand and also come with the opportunities. For this reason, in 2020, we initiate cooperation between government agency, university, research institute to work together to create a roadmap for 10 years. So at that time, NIMT responsible for quantum metrology, and we also act like a middle person that communicate between scientists and government as well. As a result, for the past 5 years, we received about 10 million US dollar, and we have a name QTRIC, which stands for Quantum Technology Research Initiative Collaboration. It's a name that represents the entire quantum technology program in Thailand. This is a few highlights. There's a university that doing ripple atoms and co-atoms. They successfully prepare optical dipole trap, and then right now they're building ripple the laser for ripple atom as well. And there's a university that do NV Center in Diamond, and they are building a magnetometer using NV Center. There's also a university that do photonic research. They design and then testing a photonic circuit. And we have a theory team as well that they study complex systems, and they also support experimentalists in terms of theory and then working together to get the work done. We also have 2 startup companies. The first one is QTFT. This is an interesting one because they actually interact with the industry in Thailand, bring the industry problem, and they will use a mathematics and optimization tool to solve the problem. And we have our EQ Tech Energy. They mostly do battery research. And that's just a highlight, but if you look at the big picture, this is the list of activity that's going on in Thailand, and NIMT also part of it as well, because what we do is quantum, because we do, maintain optical clock, and we have a quantum electrical standard. Before I talk about the quantum metrology project at NIMT, a little bit about what NIMT do. We maintain national standard for measurement, and then we make sure that any measurement in the laboratory devices or equipment has a traceability to the SI. And then we follow the ISO IEC 17025 standard. But nowadays, in metrology field, we move toward quantum standard where the quantum mechanics allow us to measure with the high accuracy and high precision, and also the definition of the unit move toward based on the universal well-defined constant. And the project at NIMT, we have 3 projects that relate to quantum. Is optical atomic clock based on trap ion, and we have just and voltage standard quantum Hall system. As for the atomic clock, is based on we have clock oscillator that use a feedback loop to stabilize the bit frequency to atomic transition frequency. And the project at NIMT, we actually, it's because of COVID-19. We cannot, during that time, we cannot collaborate with Singapore. So we actually built a trap at NIMT. And this is a trap that I and my colleague designed by ourselves and built it in-house. And we successfully trapped ytterbium ion. And right now we can do excess motion measurement, experiment control, and do some microwave spectrography. As for the Josephson junction voltage, we have 2 superconductor and then as an insulator in between, and use the effect to generate voltage. And since 2005, we have the old system, but because of program and funding, we upgrade to the programmable version of Josephson junction that we can bias the current as a different segment, and then we get the program voltage output in a programmable way. And based on this, we can build an AC quantum voltmeter, use a PJVS, and combine with the sampler, we can calibrate the AC voltage source up to 100 kilohertz. As for the quantum Hall resistance, we also have material based on gallium arsenide that is working for the past 10 years. And this is our result example. But nowadays we're gonna test a graphene sample, which we design the mounting of sample, and then we would like to move to the AC quantum Hall because right now we only calibrate the DC resistance. But if we want to go to AC, frequency dependence on impedance, and this is the way to go. So besides from the quantum metrology project, there's another thing I would like to mention is another role of NIMT is based on something on this workshop last year, that adoption of quantum technology might need or benefit from metrology. The idea is following. So for the past decade, quantum metrology field benefit from quantum because we use quantum effects to do precision measurement. But to put quantum technology to make real impact in industry, in the workshop there's the concept of called quantum metrology for quantum, where the manufacture or mass production of quantum technology component and things is very expensive. So to scale it up, we might need standardization, and standardization is a lot of process. There's a terminology, testbed, and a document and things like that. For NIMT to prepare to this trend, we also have a project under NQI. It's a National Quality Infrastructure. It's a single photon metrology where we calibrate a single photon detector against the standard detector. And this is a collaboration of the university, and also we send people to learn from PTV. I think it's a time synchronization. QKD system network require precise time synchronization. And NIMT right now explore the possibility of using wide rapid technology to synchronize in the network down to better than nanosecond, and that might be beneficial for the large or distributed QKD. And not only the project at NIMT, so we also have a chance to interact with people from the university that doing co-add-on research. I personally have a chance to build an atomic vapor cell by myself, and it's quite good. So the result is we have a skill and knowledge to build an atomic vapor cell. And also right now we do a proposal to build an electric field sensor based on the Rydberg atom by measuring ultra-high splitting. So at NIMT in the future, it might provide reference RF field for testing their device, and our RF probe that for cell, the vapor cell characterization. So that's the overview of our activity that relate to quantum technology at NIMT. But in the end of the day, we just part of the big picture. And in the end of the day, it comes down to people, scientists, engineers that work together, and also support from the government as well. And I personally hope that in the future we have a chance to interact with the researcher more, so that we can work together to develop our communities. So that's all. I would like to thank our NIMT staff that provide me information about the research, and also researcher in Q-Trade that I have chance to interact and learn from them. So that made this presentation possible, and all the government funding agency. Thank you.
Thank you for taking a lot of time. And so we are open for comments. So from all right, so
just a quick question: do you have industries decided that funds like visions?
In terms of hardware, we don't have, but only the startup that I mentioned that they use explore the quantum algorithm for industry.
So among all the technologies that we have shown, which one do you think has more priority? Because it looks like you're doing almost kind of
In terms of priority, actually, right now in terms of metrology, the voltage and resistance we almost reached the limit where the customer they send the device their equipment, and that precision of that equipment is just 10 times above worse than our primary standard. So in the near future, they will get better, but we have to catch up by improving our system. I would say voltage and resistance.
all right. Okay, so let us thank all the speakers for the session. We can gather for the next session in 10 minutes. 2:24.
또는 가보셔야 돼요.